Imagine you are lying on your back in a dark field at night. The air is cool, the earth beneath you still holding a little warmth from the day, and above you, there it is, the sky, a black canvas scattered with more lights than your eyes can possibly count. Some twinkle, some seem steady, and among them, a faint river of haze stretches across the heavens, the Milky Way. What you're seeing isn't just pretty scenery. Each of those dots is a star, some bigger than our sun, some smaller, many unimaginably far away. And that hazy band, the Milky Way, is actually billions of stars packed together in our home galaxy. If you could somehow stand outside of it, you'd see a spiral structure, elegant arms coiled like a cosmic pinwheel. The Milky Way contains perhaps 100 to 400 billion stars, and around many of those stars, planets circle, unseen to our naked eyes. Here's a humbling thought. If you could travel at the speed of light, 300,000 kilometers per second, it would still take you 100,000 years to cross the Milky Way from one side to the other. And our galaxy is just one among 2 trillion others that astronomers estimate exist in the observable universe. But let's step back, because to understand space, you need to begin closer to home, with Earth, the Sun, and our cosmic neighborhood, the solar system. The Sun, that bright ball of fire you see every day, is a star. But it isn't just any star to us. It's the star, the one whose gravity holds the entire solar system together. Everything we know, our planet, the moon, the other planets, the asteroids and comets, all of it is locked in a gravitational dance around the sun. The sun itself is enormous. You could fit about 1.3 million Earths inside it. It's made mostly of hydrogen and helium, and in its core, nuclear fusion reactions roll endlessly. Every second, it fuses about 600 million tons of hydrogen into helium, releasing energy that eventually travels through space to warm Earth and light up our skies. Without that energy, Earth would be an icy, lifeless rock. Now, zoom out a little. Orbiting the sun with us are 7 other major planets. Mercury, small and scorched, hugs the star closely. Venus, Earth's twin in size but not in habitability, hides beneath toxic clouds. Then there's Earth, our blue marble, and Mars, red and dusty, where robotic explorers crawl today. Beyond them lie the giants: Jupiter with its swirling storms, Saturn with its stunning rings, Uranus tilted on its side, and Neptune, deep blue and windy. Each planet has its own set of moons, rings, and mysteries, making our solar system a miniature universe in itself. And yet, it is just one solar system among billions. Astronomers have already confirmed more than 5,000 exoplanets orbiting other stars, and the real number is almost certainly in the hundreds of billions. Some of them are hot Jupiters, massive gas worlds orbiting so close to their stars that a year lasts only a few days. Others are rocky worlds like Earth, perhaps with liquid water, perhaps with life. We do not know yet, but we are searching. Still, even with all this knowledge, we've only begun to scratch the surface. Space is more than planets and stars. It's black holes, pulsars, galaxies colliding, time warping, light bending, and mysteries we have yet to even imagine. But for now, take one last look up at that field of stars in your mind's eye. Remember, when you see starlight, you're looking back in time. The nearest star after the sun, Proxima Centauri, is 4.2 light years away. That means the light you see left that star more than 4 years ago. Some of the stars you see are hundreds, even thousands of light years away. The universe is a time machine, and every night sky is a record of ancient history. If the universe is a stage, then the solar system is just a tiny spotlight on it. Beyond the planets lies an enormous, mostly invisible frontier. You might imagine space is empty, but it isn't really. It's full of faint traces, radiation, dust, magnetic fields, and particles moving at incredible speeds. First, let's look at the edges of our neighborhood. Past Neptune, the solar system doesn't simply end. Instead, it stretches into a mysterious region filled with icy bodies, the Kuiper Belt. Think of it as a cosmic junkyard, leftovers from the early days of planet building. Pluto lives here, along with other dwarf planets like Eris, Haumea, and Makemake. They're frozen relics, carrying chemical secrets of the solar system's youth. Even farther out lies the Oort cloud, a hypothetical sphere of icy objects surrounding the solar system at distances so vast that a single orbit could take millions of years. Scientists believe it's the birthplace of long-period comets, the ones that appear once in a human lifetime, blaze across the sky, and vanish again into the dark. But what lies beyond even that? The answer: interstellar space. In 1977, NASA launched the Voyager 1 and Voyager 2 probes. Decades later, both have left the protective bubble of the sun's magnetic field, called the heliosphere, and entered interstellar space. Voyager 1, now over 23 billion kilometers from Earth, still whispers faint radio signals back to us. It carries a golden record, literally a gold-plated disc, with sounds and images from Earth. Greetings in dozens of languages, music, even the sound of a kiss. A message in a bottle drifting through the ocean of stars. Space itself isn't flat and static. It bends, stretches, and grows. This is where things get truly strange. You've probably heard that the universe is expanding, but what does that mean? Imagine a loaf of raisin bread rising in the oven. As the dough expands, the raisins all move farther apart. No single raisin is the center of the expansion. The dough itself stretches. Our universe works like that. Galaxies aren't flying through space so much as space itself is growing between them. This discovery traces back to the 1920s, when astronomer Edwin Hubble observed that distant galaxies are all moving away from us. The farther away a galaxy is, the faster it recedes. This was shocking evidence that the universe is not eternal and unchanging. It had a beginning. That beginning is what we call the Big Bang. Now, despite its name, the Big Bang wasn't an explosion in space. It was the rapid expansion of space itself from an unimaginably hot, dense point. Time, matter, energy, all of it began there 13.8 billion years ago. Every star you see, every planet, every atom in your body, all trace their origin to that fiery birth. The calcium in your bones, the iron in your blood, the oxygen you breathe, all forged later in the cores of stars that lived and died billions of years ago. As astronomer Carl Sagan once said, "We are made of star stuff." But here's a puzzle. If the universe began from a tiny singularity, what lies beyond it now? Does the universe go on forever, or does it curve back on itself like the surface of a sphere? Scientists don't know. What they do know is that the expansion isn't slowing down as one might expect from gravity. It's speeding up as though some mysterious force is pushing galaxies apart. That force has been given a name: dark energy. Dark energy makes up about 68% of the universe. Add to that 27% dark matter, which doesn't emit light, but reveals itself through its gravity, and you're left with a shocking fact. The stuff we can actually see Stars, planets, gas, dust makes up less than 5% of everything. So next time you gaze up at the night sky, remember this. The universe is mostly invisible, filled with forces and particles we barely understand. The stars you see are like fireflies on the shore of a vast, dark ocean. Stars are the engines of the universe. Without them, space would be silent and cold, a sea of dark matter with no light to pierce it. They are born, they live, and they die, and in their death, they create the very elements that make life possible. So how does a star begin? Picture a vast cloud of gas and dust floating in space called a nebula. These are stellar nurseries, places where stars are born. Gravity begins to tug on the particles, pulling them together. As the cloud contracts, it heats up. Deep in its heart, pressure builds until hydrogen atoms are squeezed so tightly they fuse into helium. At that moment, a star is born. Our sun began this way 4.6 billion years ago. Right now it's in its stable middle age, quietly burning hydrogen in its core. This stage, called the main sequence, can last billions of years. For the sun, it's about a 10 billion year journey, and we're roughly halfway through. But not all stars are the same. Some are small, cooler, and red, so-called red dwarfs. They burn their fuel slowly, living for trillions of years, far longer than the current age of the universe. Others are massive blue giants, burning furiously and dying young, sometimes in just a few million years. The fate of a star depends on its mass. Our sun, when it runs out of hydrogen, will swell into a red giant, expanding so much that it may swallow Mercury and Venus, perhaps even Earth. Its outer layers will drift away into space, forming a glowing cloud called a planetary nebula, while the core will shrink into a small, dense remnant, a white dwarf. Imagine something the size of Earth, but with the mass of the sun, so dense that a teaspoon of its material would weigh as much as a car. Over trillions of years, the white dwarf will slowly cool, fading into a black dwarf, a cosmic cinder. But for massive stars, the story is more dramatic. When they run out of fuel, their cores collapse under gravity's crushing weight. The result? A supernova, a colossal explosion that can outshine an entire galaxy for weeks. These explosions scatter heavy elements like iron, gold, and uranium into space. Without supernovae, planets like Earth could not exist. Every atom of iron in your blood, every atom of gold in a wedding ring was born in the heart of a dying star. Sometimes, the collapsing core becomes a neutron star, an object so dense that a single teaspoon of its matter would weigh billions of tons. Some neutron stars spin rapidly, shooting beams of radiation into space. These are called pulsars, and they blink rhythmically like cosmic lighthouses. If the star is truly massive, even stranger things happen. The collapse continues until not even light can escape. A black hole is born. Black holes are the ultimate paradoxes of the universe, objects so small yet so powerful that they warp space and time itself. Near their event horizon, the boundary of no return, gravity is so strong that time slows down compared to the outside world. To an outside observer, an object fallen in would appear to freeze in time, and yet black holes may not be eternal prisons. In the 1970s, physicist Stephen Hawking proposed that they slowly leak energy, a process known as Hawking radiation, and may eventually evaporate over unimaginable timescales. Stars, then, are not just pretty points of light. They are the cosmic forges, shaping galaxies, creating the ingredients of life, and bending the very fabric of reality. To look at the stars is to look at the universe in motion, to witness a cycle of birth, brilliance, and death that spans billions of years. And here's the wildest part. Every single star you see in the night sky is inside our own Milky Way. The faintest galaxies visible to the naked eye, like Andromeda, are so far away that their stars blur together into a hazy patch. In other words, when you look up, you're not even scratching the surface of what's really out there. If stars are like people, then galaxies are their cities. They are vast cosmic communities, each one containing hundreds of billions of stars, along with gas, dust, dark matter, and untold numbers of planets. Our home galaxy, the Milky Way, is a spiral galaxy. From Earth, we see it edge on. So it appears as that hazy band of light across the sky. But if you could fly far above it, you'd see a pinwheel shape, with long arms curling out from a bright central bulge. In those arms are young, blue stars being born in clusters, while older, redder stars live closer to the center. The Milky Way is huge, about 100,000 light years across. That's so big that if you could travel at the speed of light, it would take you 100,000 years to cross from one side to the other. And yet, in the scale of the universe, it's just an average-sized galaxy. There are giant elliptical galaxies that are far larger, containing trillions of stars. There are tiny dwarf galaxies with only a few billion stars. Some galaxies are irregular, distorted by collisions and gravitational encounters. In fact, galaxies often collide. Take our nearest neighbor, the Andromeda Galaxy, which lies about 2.5 million light-years away. Right now, it's a faint smudge in the night sky. But astronomers have discovered that the Milky Way and Andromeda are on a collision course. In about 4 billion years, the two galaxies will crash together. Don't worry, stars are so far apart that individual collisions will be rare. Instead, gravity will pull the galaxies into a new shape, perhaps forming a giant elliptical galaxy nicknamed Milkdromeda. Inside galaxies are more mysteries. At their centers lurk supermassive black holes, millions or even billions of times the mass of the Sun. Our own Milky Way hosts one, known as Sagittarius, a star. Normally it lies quiet, but when gas and stars wander too close, it can flare brightly, releasing incredible energy. Some galaxies are even more dramatic. So-called quasars shine so brightly that they outshine their entire galaxies, powered by material spiraling into their central black holes. And here's the astonishing thing. Galaxies are not sprinkled randomly through the universe. They form patterns, vast filaments and walls of cosmic structure stretching across unimaginable distances. The universe on the largest scale looks a bit like a web, with galaxies strung along threads of dark matter and enormous empty voids in between. One of the most breathtaking facts about galaxies is simply how many there are. For a long time, astronomers thought the universe contained maybe 100 billion galaxies. Then, with the Hubble Space Telescope, they pointed at a tiny, seemingly empty patch of sky no larger than the head of a pin held at arm's length. After gathering light for days, the image revealed thousands of galaxies, each one filled with billions of stars. From that, scientists now estimate there may be 2 trillion galaxies in the observable universe. Each galaxy is its own island universe, a cosmic city of stars, planets, and perhaps life. If just 1 in 1,000 stars hosts a planet like Earth, then the possibilities are staggering. Somewhere, orbiting a star in another galaxy, there may be a world with oceans, mountains, forests, and skies full of unfamiliar constellations. But even this ocean of galaxies is not the whole story. The universe is not only vast in space, but also in time. When we look at distant galaxies, we see them not as they are now, but as they were millions or even billions of years ago. Light takes time to travel, so a galaxy 10 billion light years away shows us the universe when it was young. In a way, telescopes are time machines, letting us witness cosmic history unfold. And yet, despite all we've learned, the ultimate fate of galaxies and the universe itself remains uncertain. Will expansion continue forever, pulling galaxies apart until even their stars fade into darkness? Or will some deeper force change the story? For now, galaxies spin, collide, and shine, silent beacons in the dark. They remind us that we are part of something so vast, our own planet is but a grain of dust in the grand cosmic cityscape. So far, we've traveled through planets, stars, and galaxies. But to truly understand space, we need to explore the fabric that holds it all together, space-time. At first it seems simple. Space is where things are. Time is when things happen. But in the early 20th century, Albert Einstein revealed something astonishing. Space and time are not separate. They are woven together into a single fabric called space-time. Picture space-time as a vast, invisible sheet. Place a heavy object on it, like a bowling ball on a trampoline, and the sheet curves. Now roll a smaller ball across it. The smaller ball doesn't move in a straight line. It curves around the depression. That's what gravity really is, the bending of space-time caused by mass and energy. This idea is known as general relativity, and it explains why planets orbit stars, why light bends near massive objects, and even how time itself can flow differently depending on where you are. Yes, time can bend. Imagine two clocks. One sits on Earth's surface, deep in our planet's gravitational field. The other floats far out in space where gravity is weaker. The clock near Earth ticks just a little bit slower. This effect is called gravitational time dilation. Though tiny in everyday life, it becomes critical in high-precision technology. GPS satellites, for example, orbiting high above Earth, experience time slightly faster than clocks on the ground. Without correcting for this relativistic effect, GPS navigation would drift kilometers off course each day. But relativity doesn't stop there. When you move close to the speed of light, time also slows down relative to a stationary observer. This is special relativity. Imagine a spaceship traveling near light speed. To those on board, time feels normal. But to someone watching from Earth, the traveler's clocks appear to tick more slowly. This leads to the famous twin paradox. One twin takes a high-speed journey into space, then returns younger than the sibling who stayed home. Space-time also allows for mind-bending phenomena like gravitational lensing. Light normally travels in straight lines, but when it passes near a massive object, the curvature of space-time bends its path. Distant galaxies and stars can appear distorted or multiplied as though seen through a cosmic magnifying glass. Astronomers actually use this effect to study faraway galaxies and even to map invisible dark matter. Perhaps the most dramatic warping of space-time happens around black holes. Near the event horizon, gravity is so intense that time slows dramatically. To a distant observer, objects falling into a black hole seem to freeze at the edge, never quite crossing over. For the falling object itself, time flows normally, but the rest of the universe appears to race forward. And then there are gravitational waves. ripples in space-time itself. Predicted by Einstein a century ago, they were finally detected in 2015. When two black holes spiral together and merge, they send vibrations across the universe like stones dropped into a cosmic pond. These waves stretch and squeeze space ever so slightly. Sensitive instruments like LIGO, Laser Interferometer Gravitational Wave Observatory, can detect these ripples, opening a new way of listening to the universe. Here's the mind-bending part. Space-time itself is not static. It's dynamic, expanding, twisting, bending under the influence of matter and energy. We live inside this flexible fabric, carried along as it stretches. Even your body, your mass, bends space-time ever so slightly. It's a reminder that we are not separate from the universe. We don't just live in space-time, we are woven into it, part of the grand cosmic tapestry. Every second, every step, every heartbeat follows its rhythm. And yet, despite all we know, relativity hints at mysteries still unsolved. How does it fit with the quantum world of the very small? Could space-time itself be made of tiny, invisible building blocks? Might wormholes, tunnels through space-time, exist, connecting distant parts of the universe? The deeper we look, the stranger the cosmos becomes. Space is not just a backdrop. It's alive, dynamic, and filled with possibilities. Every story has a beginning, and we've traced ours back to the Big Bang. But what about the ending? What will ultimately happen to the universe itself? Astronomers don't know for certain, but they've considered several possible fates, each more haunting than the last. The first scenario is the heat death. Since the Big Bang, the universe has been expanding. Galaxies drift apart, stars burn their fuel, and energy spreads out more and more thinly. If this expansion continues forever, then eventually all stars will die. White dwarfs will cool, neutron stars will fade, and even black holes will evaporate. The universe will become a cold, dark place, filled only with thin gas and faint radiation. No energy differences will remain to fuel processes or life. This is the ultimate entropy, where everything is evenly spread out, and nothing interesting can ever happen again. A universe of silence. But there are other possibilities. Some cosmologists have wondered whether the expansion could one day reverse. If gravity overcomes the push of dark energy, the universe might begin to contract. Galaxies would start falling back together, stars would collide, and the entire cosmos would collapse into a fiery finale known as the Big Crunch. In that scenario, the universe could potentially rebound, collapsing, then exploding again in an endless cycle of bangs and crunches. Then there's the stranger idea of the Big Rip. If dark energy doesn't just push the universe apart but grows stronger over time, it could eventually tear everything apart. Galaxies would separate, then solar systems, then planets from their stars. Eventually, the pull would grow so intense that even atoms themselves would rip apart. The universe would dissolve into a soup of particles. There's even a fourth idea: vacuum decay. Physicists have suggested that our universe may be in a false vacuum, a temporary state of stability. If it ever decays into a true vacuum, the laws of physics could suddenly change. A bubble of this new vacuum would expand at nearly the speed of light, wiping out everything in its path instantly. No warning, no chance to escape. To us, it would seem like nothing happened, just existence, then non-existence. And yet, while these endings sound grim, they are unimaginably far in the future. Stars will keep burning for trillions of years. Galaxies will keep swirling for eons. Black holes will take longer than the current age of the universe squared, then squared again, to evaporate. In a way, the cosmos gives us more time than we could ever need. Thinking about the universe's fate also raises a deeper question. Why does it exist at all? Why is there something instead of nothing? We don't yet know. But in studying the cosmos, we learn not just about stars and galaxies, but about ourselves, our place in this grand, mysterious story. Here's a comforting thought. Though the universe may one day fade, right now it is bursting with energy and possibility. Stars are being born, planets are circling, galaxies are colliding. The cosmos is alive, and we are part of its fleeting, shining moment. So perhaps the real answer to the universe's fate isn't just physics, it's meaning. The atoms that will someday drift apart are, for now, together in you, in me, in every living thing on Earth. And in this brief spark of time, we get to look up and ask the questions. The end may be far off, but the wonder is here now, waiting for anyone who dares to look up. For most of human history, the stars were untouchable. They were gods, lanterns, mysteries. We could chart their patterns, use them to navigate oceans and tell stories about them, but we could never imagine reaching them. That began to change only a few decades ago. In the mid-20th century, humanity took its first fragile steps beyond Earth's cradle. Rockets, once weapons of war, became ladders to the sky. In 1957, the Soviet Union launched Sputnik 1, the first artificial satellite. A small beeping sphere, it orbited Earth and shocked the world. Suddenly, space was not just a dream, it was real, and it was political. The space race began. Just 4 years later, in 1961, Yuri Gagarin became the first human to orbit Earth. He completed a single loop in his spacecraft, Vostok 1, and when he landed, the world knew that humanity had entered a new era. His words, Poyakali, let's go, still echo as the symbolic beginning of human spaceflight. The United States responded with the Apollo program. In 1969, millions watched on flickering black and white televisions as Neil Armstrong and Buzz Aldrin stepped onto the moon. That's one small step for man, one giant leap for mankind, Armstrong said. And for a moment, all of humanity stood together on another world. The moon landings were brief, just a handful of missions, but they remain one of the greatest achievements in history. Humans walked, drove, and even golfed on the lunar surface. They left footprints that, without wind or rain, will remain for millions of years. Since then, our journey into space has continued in quieter, steadier ways. The space shuttle made space flight routine, ferrying astronauts and building the International Space Station ISS, a laboratory orbiting 400 kilometers above Earth. The ISS is a testament to global cooperation, built by 15 nations, hosting experiments in physics, medicine, and biology. Astronauts from around the world live and work there, circling the Earth every 90 minutes, watching sunrises and sunsets 16 times a day. We've also sent robots where humans can't yet go. Rovers like Spirit, Opportunity, Curiosity, and Perseverance have crawled across Mars, drilling rocks and searching for signs of life. The Voyager probes continue their lonely journeys into interstellar space, carrying humanity's golden calling card. The James Webb Space Telescope, launched in 2021, peers deep into the cosmos, showing us galaxies as they were billions of years ago. But despite all these triumphs, we've barely begun. So far, humans have only traveled as far as the moon. Mars remains a distant dream. Other planets are farther still, and the nearest star, Proxima Centauri, is so far away that with current technology, it would take tens of thousands of years to reach. And yet, dreaming is what we do best. Private companies now join the effort, building rockets that can land themselves and planning missions to Mars. Scientists imagine spacecraft propelled by giant sails catching the light of lasers, reaching nearby stars within a human lifetime. Futurists envision colonies on the Moon, Mars, or even floating cities in the clouds of Venus. Space is hard, dangerous, expensive, unforgiving, but the rewards are immense. To travel beyond Earth is to ensure humanity's survival, to gather knowledge, and to remind ourselves that we are part of something vast. When we look back on human history from some distant future, our first steps into space may be remembered as the moment we truly grew up, when we stopped looking at the sky with only wonder and began to reach for it with our hands. The journey has only just begun. When people look up at the night sky, one question rises again and again. Are we alone? The universe is vast. 2 trillion galaxies, each with billions of stars, each star with planets of its own. It seems almost impossible that Earth is the only place where life has appeared. And yet, so far we have no proof of life anywhere else. Let's start close to home. In our solar system, Earth is the only confirmed living world. But several others show promise. Mars once had rivers, lakes, maybe even oceans. Its surface today is dry and barren, but beneath its soil, there may still be water and perhaps microbes hidden underground. The Perseverance rover is searching for signs of ancient life, while future missions plan to return Martian samples to Earth. Beyond Mars lies Europa, one of Jupiter's moons. Beneath its thick shell of ice lies a global ocean, kept warm by the moon's internal heat. That ocean may contain more water than all of Earth's oceans combined. Imagine an entire hidden sea, dark and alien, possibly teeming with life. Saturn's moon, Enceladus, offers a similar promise, shooting geysers of water vapor into space. Astronomers have detected organic molecules in those plumes, hinting at chemical ingredients for life. Even Titan, Saturn's largest moon, presents strange possibilities. It has rivers and lakes, not of water, but of liquid methane and ethane. Could life exist in such exotic chemistry, utterly unlike anything on Earth? But the real explosion of hope has come from the study of exoplanets, worlds orbiting other stars. Since the first discovery in 1992, astronomers have confirmed thousands, and the number grows every year. Some are gas giants hugging close to their stars. Others are rocky worlds in the so-called habitable zone, where liquid water might exist. One of the most exciting finds is the TRAPPIST-1 system, where 7 Earth-sized planets orbit a small, cool star. 3 of them lie in the habitable zone. Imagine standing on one of those planets, looking up to see 6 neighboring worlds glowing in the sky, close enough that you could see them with the naked eye. With telescopes like James Webb, we're beginning to study exoplanet atmospheres, searching for biosignatures, clues like oxygen, methane, or other gases that might hint at life. Within a few decades, we may know whether living planets truly exist beyond our own. But what about intelligent life? That's where things get stranger. For decades, scientists have scanned the skies with radio telescopes, listening for signals, an effort known as SETI, the search for extraterrestrial intelligence. So far, nothing has been confirmed, just silence. This silence has a name: the Fermi paradox. With so many stars and planets, why haven't we found signs of other civilizations? Where is everyone? There are many possible answers. Maybe intelligent life is rare. Maybe civilizations rise and fall quickly, too brief to overlap with ours. Maybe they're out there but too far away, or using technologies we don't yet understand. Or maybe they've chosen not to contact us, like watching ants from a distance without interfering. And yet, even without answers, the search continues. Because if we do find life, whether a microbe on Mars or a signal from another star, it will change everything. It would mean we are not alone, that life is a common thread woven into the universe. Until then, we listen, we look, we wonder. Every telescope pointed at the stars is, in some way, asking the same question humanity has whispered for millennia. Who else is out there? Space is beautiful, yes, but it's also deadly. Beyond the glitter of stars lies a universe filled with hazards that could destroy planets, extinguish civilizations, and reshape galaxies. Start with something close to home: asteroids and comets. Earth circles the sun in a crowded neighborhood. Millions of space rocks, leftovers from the birth of the solar system, still orbit with us. Most are harmless, but some cross Earth's path. 65 million years ago, one such asteroid, about 10 kilometers wide, slammed into what is now Mexico's Yucatan Peninsula. The impact unleashed energy equivalent to billions of nuclear bombs. It caused wildfires, tsunamis, and a nuclear winter that darkened the skies. Dinosaurs, dominant for 160 million years, vanished almost overnight. Only small, adaptable creatures, including our distant mammalian ancestors, survived. Smaller asteroids hit more often. In 1908, a meteor exploded over Tunguska, Siberia, flattening thousands of square kilometers of forest. In 2013, a meteor streaked over Chelyabinsk, Russia, shattering windows and injuring more than 1,000 people with flying glass. NASA and other agencies now scan the skies constantly, tracking near-Earth objects. They have even tested ways to deflect one. In 2022, the DART mission successfully nudged a small asteroid's orbit, a first step in planetary defense. But rocks are only one threat. Space is drenched in radiation. Our sun sometimes flares violently, blasting streams of charged particles across the solar system. On Earth, our magnetic field shields us, but astronauts outside that protection would be vulnerable. A powerful solar storm could also fry satellites and knock out power grids. In fact, in 1859, the Carrington event, the strongest solar storm on record, sparked fires in telegraph offices and lit up auroras as far south as the Caribbean. If such a storm struck today, our technology-dependent civilization could suffer catastrophic damage. Beyond our sun lie even deadlier events. Supernovae, the explosions of massive stars, can unleash radiation bursts strong enough to strip a planet's atmosphere. Fortunately, there are no nearby stars close to going supernova, but farther away, another danger lurks: gamma ray bursts. These are the universe's most powerful explosions, lasting seconds, but releasing more energy than our sun will emit in its entire lifetime. If one happened close enough and was aimed at Earth, it could devastate our ozone layer and trigger mass extinction. And then there are black holes. They are not cosmic vacuum cleaners sucking everything in at random, but if a star wanders too close, it can be shredded, its gas spiraling into a brilliant disk of light before vanishing beyond the event horizon. Thankfully, no rogue black holes threaten us right now, but Astronomers believe millions may wander invisibly through our galaxy. Even on the largest scales, danger exists. Galaxies collide, as ours will with Andromeda. Stars are flung from their orbits, planetary systems disrupted. Over billions of years, entire galaxies merge, reshaping the cosmos. The greatest threat, though, may be invisible: time itself. Eventually, every star will fade, every galaxy will dim, every atom may decay. Against such cosmic forces, Earth is fragile, temporary, and yet, knowing these dangers doesn't diminish our wonder, it deepens it. We are fragile, yes, but we are aware. We are a species that can study asteroids, track solar storms, imagine gamma-ray bursts, and even plan defenses. That awareness is our strength. The universe is dangerous, but we are learning to face it. Perhaps in the distant future, humanity, or its descendants, will spread among the stars, building civilizations that can withstand supernovae, black holes, even the death of galaxies. Until then, Earth is our safe harbor, fragile but precious, and worth protecting against the hazards of space. For all that we've learned about space, perhaps the most powerful force driving us outward is not technology or science, but imagination. Long before rockets, long before telescopes, people dreamed of traveling beyond Earth. Ancient myths spoke of flying chariots and gods among the stars. Writers like Jules Verne and H.G. Wells imagined journeys to the moon and Mars decades before the first spacecraft left the ground. Science fiction became the playground of cosmic dreams, starships crossing galaxies, alien civilizations, faster-than-light drives and wormholes. For much of history, these were fantasies, but often what begins as fiction later inspires reality. Take the idea of space stations. In the 1920s, the visionary Konstantin Tsiolkovsky imagined giant wheels orbiting Earth, habitats where people could live and work. Decades later, the International Space Station brought that dream into being. The flip-open communicators in Star Trek look remarkably like early flip phones, and the robotic rovers that crawl across Mars resemble machines once drawn only in pulp magazine illustrations. But science fiction also pushes us further, daring us to imagine technologies not yet possible. One idea is the warp drive, a concept that bends space-time itself. Instead of moving faster than light, which physics forbids, a warp bubble would contract space in front of a ship and expand it behind, carrying the vessel across vast distances without breaking the cosmic speed limit. In fact, physicists like Miguel Alcubierre have even published papers on how such a drive might work, though it would require exotic forms of energy far beyond our reach. Then there are wormholes, tunnels through space-time connecting distant points. First described by Einstein and Nathan Rosen, they remain theoretical, but they've become a staple of science fiction. Could they exist? Possibly. Could they be stable long enough for travel? That's another matter, but the idea itself keeps our imaginations alive. Another vision is the Generation Ship, a massive spacecraft where entire communities live and die as it travels between stars, taking centuries to reach its destination. Or perhaps we might one day build Dyson spheres, vast structures encircling stars to capture their energy, providing power for advanced civilizations. Even communication across the stars is a dream worth chasing. If faster-than-light travel is impossible, perhaps faster-than-light messaging exists. Quantum entanglement, where particles remain mysteriously linked across vast distances, tempts us with the idea, though current physics says it can't transmit usable information that way. Still, imagination continues to press on the boundaries of what we think is possible. And yet, maybe the greatest dream is simpler: to stand on another world, look up, and see Earth as just a pale star in the sky. Astronauts describe a powerful shift in perspective when they see our planet from orbit, the overview effect. Suddenly, borders, conflicts, and divisions seem trivial. Earth is fragile, blue, and alone in the dark. Imagine how much stronger that feeling would be when looking at Earth from Mars or from the moons of Jupiter. Imagination drives exploration. Every rover, telescope, and spacecraft began as a dream in someone's mind. Every mission to space is a reminder that today's science fiction can become tomorrow's science fact. We are not there yet. The stars are still far away, and the physics of light speed is stubborn. But human history is full of once impossible feats: flight, electricity, the harnessing of fire. Each step seemed magical until it wasn't. Perhaps one day, children born on distant worlds will look up at alien skies, and for them the idea of Earth will feel like a myth, an ancient homeland across the stars. Until then, we dream, and dreaming may be the most important step of all. Space is not just a scientific frontier, it is a mirror reflecting humanity's deepest fears, hopes, and questions. For millennia, people have looked up and tried to make sense of the stars, connecting dots to form constellations, telling stories about gods, heroes, and monsters. The patterns in the sky were a way to navigate, to measure time, and to understand our place in the cosmos. The ancient Greeks mapped the heavens and created myths to explain the movements of planets and stars. Orion the hunter chased the Pleiades across the night sky. Cassiopeia, the vain queen, spun eternally in her chair among the stars. These stories were more than entertainment. They encoded knowledge about seasons, navigation, and celestial cycles. Across the world, different cultures built their own cosmic maps. The Mayans observed Venus with such precision that their calendars predicted its rising and setting decades in advance. The Polynesians navigated vast oceans using the stars as guides, remembering the positions of constellations and their seasonal shifts. Space became both a canvas and a tool, shaping societies in ways that still resonate today. Art and literature have long reflected humanity's fascination with the cosmos. From Van Gogh's swirling night skies to the epic poems of Homer describing the heavens, space has inspired creativity, wonder, and introspection. In modern times, films and books project our dreams and fears onto the universe. Alien civilizations, rogue planets, apocalyptic comets, and journeys to distant worlds. Each story reminds us of both our fragility and our courage. Philosophy, too, has been shaped by the stars. Carl Sagan spoke of the pale blue dot, reflecting on how tiny and fragile Earth is in the vast cosmic ocean. Philosophers ask, if the universe is so vast and life is so rare, what does it mean for morality, purpose, and existence? Are we alone? Or is life a common thread waiting to be discovered? These questions are timeless, and space keeps expanding their horizons. Religion and spirituality have often looked skyward. Celestial events, solar eclipses, comets, meteor showers, have been interpreted as divine messages or omens. Even today, the sight of a rocket ascending toward the stars evokes awe, a reminder that humans are reaching beyond themselves, striving to touch something infinite. Science, imagination, and culture intersect when we consider the overview effect experienced by astronauts. Seeing Earth from orbit transforms perspective, collapsing national, cultural, and personal boundaries. The planet becomes a single, interconnected system, highlighting both our vulnerability and our unity. This experience has inspired art, poetry, and renewed commitment to preserving our fragile home. Space is also a source of metaphors for human life. Stars burn bright and die, galaxies collide and reshape themselves, black holes swallow light and time. These cosmic patterns echo in literature, philosophy, and daily reflection, reminding us of impermanence, resilience, and wonder. Ultimately, the study of space is not just about planets, stars, or galaxies. It is about meaning. It shapes how we think, how we create, and how we dream. Each discovery teaches us not only about the universe, but about ourselves. Looking up at the stars, we see a mirror, vast, mysterious, and beautiful. And in that reflection, we find both humility and inspiration. Dreaming about space is one thing, reaching it is another. Human ingenuity has turned imagination into engineering, building machines that pierce the sky, orbit the Earth, and journey to other worlds. It all begins with rockets. To leave Earth, a spacecraft must overcome gravity, which requires tremendous energy. Rockets burn fuel to produce thrust, propelling themselves upward in a controlled explosion. The Saturn V rocket, which carried Apollo astronauts to the moon, remains one of the most powerful ever built, standing taller than a 36-story building and producing enough thrust to lift 140 metric tons of payload into orbit. Rockets are more than brute force. They are precision engineering. Multi-stage designs allow one section to burn and detach, making the craft lighter and more efficient. Innovations like reusable rockets, pioneered by companies such as SpaceX, reduce costs and make repeated spaceflight possible, transforming the economics of exploration. Once in orbit, spacecraft rely on orbital mechanics, understanding how gravity, momentum, and velocity interact allows satellites and probes to coast along predictable paths. Small adjustments, called burns, can change a spacecraft's trajectory, sending it to the moon, Mars, or even interstellar space. Observing the cosmos requires more than traveling to it. It demands instruments that see beyond human vision. Telescopes are our eyes into the universe. Ground-based observatories like Mauna Kea and the Very Large Telescope in Chile peer deep into space using massive mirrors and adaptive optics, which correct for atmospheric distortion. Above the atmosphere, space telescopes like Hubble and James Webb capture light unfiltered by Earth's air, revealing galaxies billions of light years away and probing the atmospheres of exoplanets. Beyond optics, humanity explores space across the electromagnetic spectrum. Radio telescopes detect invisible signals from distant stars and galaxies. Infrared instruments reveal newborn stars hidden in dust clouds. X-ray and gamma-ray detectors uncover the violent processes of black holes, neutron stars, and supernovae. Each wavelength provides a different perspective, like adding colors to a cosmic painting. Exploration also requires robots. Rovers, landers, and orbiters extend our reach to worlds humans cannot yet safely visit. Curiosity and perseverance traverse the Martian surface, analyzing rocks, drilling into soil, and searching for signs of past life. The Voyager probes, launched over 40 years ago, now sail through interstellar space, carrying our messages and observations to the cosmos. Even communication across space is a marvel. Signals travel at the speed of light, which is fast, but the distances are so vast that messages can take years to reach their destination. NASA's Deep Space Network uses enormous antennas on multiple continents to maintain contact with spacecraft at the edges of the solar system, ensuring data flows back to Earth. Powering these missions also demands creativity. Solar panels capture sunlight even in deep space. Radioisotope thermoelectric generators convert the decay of plutonium into electricity for spacecraft too far from the sun. Propulsion systems evolve, from chemical rockets to ion drives, which produce gentle but long-lasting thrust, ideal for deep space travel. All these technologies combine to make humanity a species capable of leaving its home planet. They transform dreams into reality, enabling us to touch other worlds, study distant galaxies, and perhaps one day live among the stars. The cosmos is vast, but with imagination, engineering, and perseverance, we have begun to reach out. Every spacecraft, telescope, and satellite is a step toward understanding not just the universe, but ourselves. Traveling through space is thrilling, but it is also profoundly challenging. Space is not a friendly environment. It is a vacuum, near absolute zero in some regions, filled with radiation and devoid of breathable air or gravity as we know it. Every human who ventures into orbit must adapt to conditions that our bodies evolved not to endure. The first challenge is microgravity. In orbit, astronauts experience weightlessness. At first, it feels like flying, floating freely, somersaulting through the cabin. But the human body is designed for gravity. Prolonged weightlessness causes muscles to weaken and bones to lose density, a condition known as spaceflight osteopenia. Astronauts combat this with rigorous exercise regimens using specially designed treadmills, resistance machines, and cycling devices. Even small actions like pushing off a wall require careful planning to avoid floating into equipment or teammates. Circulation and fluids also behave differently in microgravity. Blood and other bodily fluids shift toward the upper body and head, causing facial puffiness and pressure in the skull, sometimes affecting vision. Long-duration missions must account for these effects, especially for potential trips to Mars or beyond, where astronauts could spend years in reduced gravity. Space is also psychologically demanding. Isolation from Earth, confinement in small quarters, and the constant hum of machinery can challenge mental health. Astronauts rely on careful scheduling, personal routines, and communication with loved ones to maintain morale. They also train extensively to solve problems cooperatively, because in space, mistakes can be deadly. Radiation is another invisible threat. Outside Earth's protective magnetosphere, cosmic rays and solar particles bombard astronauts. Over time, this exposure increases the risk of cancer and other health issues. Spacecraft shielding and careful mission planning help, but radiation remains a fundamental limit on long-term space travel.